Okay, so we have a quiz today, and then normally we would have another quiz 2 weeks from today, but 2 weeks from today we don't have class, so instead we have one next week. So this is the one time we have a quiz today. We have a quiz next Thursday, so just be aware of that. We'll do the quiz in the last 15 minutes of class or something. So we've been talking about 2D projectile motion. We did maybe one example of that so far. Has anybody, I know probably a lot of people haven't gotten to those homework problems yet, but does anyone have any homework questions? Yes. Yeah, like any one of them. Anybody have the vectors assignment with them? I don't have it with me up here. Okay, so vectors number 2. So the first vector is like this. It has a length of 3.8, and it makes an angle of 20 degrees with the horizontal. And we want to add that to this vector. Oh, no, sorry. I did that wrong. This vector goes like this. I just did the length wrong. The length of this one is 4.5. And the length of this one is 3.8. And this one makes an angle with the vertical of 15 degrees. And we want to add those two vectors in two different coordinate systems. So first we'll do it in the coordinate system we're most used to. And then second we'll do it in a coordinate system like this. Okay. So for part A, this vector, so the key idea here is with the vectors, those don't rotate. Like this vector never changes from this orientation. And then the coordinate system, whatever coordinate system it is, you just take the tail and put it at the origin of that coordinate system. Okay, so this vector has a length of 4.5. This is x, this is y. This angle is 20 degrees. And the other vector, this is x, this is y. Put the origin at the tail of the vector. This one makes an angle of 15 degrees with the vertical. Okay, so this one over here, to calculate that, that's going to be length of that vector, 4.5, times the cosine of 20 degrees. And then the y component is 4.5 times the sine of 20 degrees. And could someone punch those? Oh, maybe I have it here. Okay, so this should be 4.229, 1.539. And this other vector, okay, and let me slow down. So the 20 degrees I use here is because you always start at the positive x-axis and go counterclockwise to get to the vector. So that's 20 from here. This one isn't going to be 15. For this one, you have to go around to go counterclockwise from the positive x-axis to here. You have to go 270 plus 15, or you can go negative 65, and it'll give you the same thing either way. So the angles can be 285 or negative, no, 75, sorry, negative 75. To calculate that, it's the length, 3.8, times the cosine of 285, and 3.8 times the sine of 285. And for that one, you get 0.984, negative 3.671. Okay, so first of all, and I'm just going to add those now, but let's look at these two. Sanity check the answers that came out of the calculator. Does it make sense that both of these components are going to be positive? Yeah, because it's in the first quadrant. Does it make sense that this is positive, negative? Yeah, because it's in the fourth quadrant. So now we'll add these. We're just going to take 4.229, 1.539, plus 0.984, negative 3.671. And to add them, get the x component of the resultant vector. You just add the x components. 4.229 plus 0.984 is 5.213. And then the y component, 1.539 plus a negative 3.671 is negative 2.132. And so that's the answer. And now we're going to do the same thing in this new coordinate system. And I want to point something out right now. Notice that this x-axis is just in our old negative x direction. And this y-axis is in our old negative y direction. So we're going to go through the steps again, but I just want you to notice that we expect that the answer for this coordinate system, both components, is just going to be opposite of this. So we're going to get, when we go through all the steps, do all the calculations, we're just going to get negative 213, positive 2.132. Yep. No, never mind, sorry. Oh, okay. It would be negative 75. Okay. Great. Okay, so for part B, so now we have a coordinate system like this. Our vector, now this is a place where people make mistakes pretty often. The vector doesn't rotate. Like you can think of the coordinate system as having rotated, but you don't rotate the vector. The vector is still just, it still points the same way. The vector doesn't care what we do with the math. The vector just lives there in the world. Yep. For which one? Hmm. Oh, well, so this is so where I write the x and the y, that's the positive direction. I just drew this negative side out just so you could see the relationship. So yeah, the positive x is going this way. And this angle is 20 degrees. And then the second vector is like this, and this angle is 15 degrees. So for the first one now, start at the positive x-axis, which is over here now, and go counterclockwise to get there, to get to the vector. So 90, 180, plus 20, that's 200 degrees. So we have 4.5 times cosine of 200, 4.5 times the sine of 200, and that gives negative 4.229, negative 1.539. And then for the second vector, start at the positive x-axis and go counterclockwise. Here's the positive x-axis. So you go 90 to get there, plus another 15, so 105 degrees. So we have 3.8 times the cosine of 105 and 3.8 times the sine of 105. And you get negative 0.984, 3.671. Okay, before I add these, let's sanity check this again. Now this can be a little confusing. Does it make sense that these are both negative? Yeah, you're sort of used to thinking of this as the first quadrant, but it's not anymore. The first quadrant is over here between the positive axes. This is the second, this is the third quadrant, so it makes sense that they would both be negative. And for this one, does it make sense that it's negative positive? Yeah, first quadrant, second quadrant, so that's negative x, positive y. And then adding those, negative 4.229, negative 1.539, plus negative 0.984, positive 3.671. And you get negative 5.213, 2.132, which is exactly opposite of what we got in part A. And the reason for that is that the axes are both exactly opposite of what they were before. If you rotate it 90 degrees, x switches to y, y switches to x, and one sign switches. Yeah. Yeah. If you're going to go positive, it's always counterclockwise. If you go clockwise, it's negative. So yeah, this one I could have called this negative 160 degrees, and it would have worked out the same. And this one I could have called it, well, that would have been a big angle, 180, 270 minus, so negative 255 would have worked out the same. Any other questions about this one? Any other homework questions? Okay, so now we're on to common misconception number 2 in this class. And I'm going to say this in a way that doesn't seem very like intuitive related. I'll try to connect it to the, yes. No, everyone leaves. Common misconception number 1. Yes, that's right. A while ago. Yep. We're not going to have too many of these. Yes. Common misconception number 2 um, is that the x component, of um, directional quantities affect the y components and vice versa. This is sort of a funny wording. There's got to be a better way to say this, but I'm going to give an example that shows what I'm talking about. And vice versa. Okay, so this is what people often, seem to intuitively believe. Yes, question? Oh, well, that's true. Yeah, that's true. I think the example that I give is going to be something that people would have sort of a strong physical uh, idea about that's wrong. Um, but the way I say it, like, yeah, who has a strong physical idea about that? Nobody. No one's ever thought about it in that way before, really. But I didn't really know how else to say it, so that's what I'm going to talk about. Yeah, that's the example I'm going to use. Um, so here's the truth. Um, the motion of objects in the x direction has no bearing on the motion of objects in the y direction. Motion. Yeah. Okay, so here's the example that I'm going to use to. So this is something that, like, if everybody in here was asked what would happen in this example, most people in the class would get this wrong. So let's say so one person has a gun. They're squinting to aim. And this other person is holding a bullet. Okay, and they're holding them right at the same height. These people both have to be bald. This one might possibly be a monkey of some kind. And at the same instant, this guy shoots this gun horizontally, and this guy drops this bullet to the ground. Okay. Most people, if you haven't heard of this example before, you kind of have this feeling that something about the fact that it's going so fast horizontally keeps it from falling to the ground as fast. This bullet, so if you measured really carefully when these two bullets hit the ground, this one would hit the ground way before this one did. The truth is that they hit the ground at exactly the same time. The bullet just hits the ground a long way away. And I think maybe where that intuition comes from is like, if you think of what would happen in any normal space, like if I shot a bullet here, all you would see is that I basically just made a hole in the door at roughly the same height that I shot it. And you get the sense that it wasn't really falling at all. It's just going in a straight line. But the truth is, it is falling just as fast as this is. It's just going so fast horizontally that by the time it falls, you can't see it anymore. You know, by the time it hits the ground. Yep. That's right. And there are some, that's true with a bullet, and I'm going to show a video of that. There are some things where it's not true, like a frisbee, you know. And that, but when that happens, that's all air resistance, air related effects. Okay, so a frisbee stays up because of air effects. It lowers the pressure above it, and so the air pushes it up the same way like an airplane does. But if you get rid of air effects and bullets, like the air basically slows it down horizontally, but it doesn't really slow it down much vertically. And so these two, you can just do this experiment if you're careful, and they'll hit the ground at the same time. One thing that's sort of funny about this is, well, what if you have to be really careful about it, not just because you could shoot somebody. Okay, that's one reason. And also you have to make sure that they're released at the same time, and that's hard to coordinate. But you also have to make sure that this is firing exactly horizontally, because even if you just slightly raise it up or down, it'll have a drastic effect on how long it takes for this to hit the ground. And I'll do a example calculation of that after we're done with all this. You still have a question? It doesn't. I mean, I wouldn't know that ahead of time, but I know that it. Well, do all like do all guns spin the bullet, or is that? Uh-huh. But like shotguns don't spin. Okay. Well, yeah. So, anyways, what I'm going to show is with a pistol. So I guess it's spinning then, right? Because it's just a single bullet, and yeah, you might think that that does the same thing that a frisbee does. Turns out it doesn't. You know. Um, so these bullets will hit the ground at the same time. Exclamation point. Right. So let's watch this video because I know you don't believe what the math says about it. You know, see if we can identify what it is about the math that says these two are going to be the same. Okay, so let's say that both are dropped from a height of 1 meter. Or you know, the one's fired horizontally from a height of 1 meter, and the other one's dropped from 1 meter. So let's say, okay, fired horizontally from 1 meter versus dropped from 1 meter. And we're going to calculate the time required to hit the ground. Okay, so A, let's just do the dropped one first. Okay. This is a problem that we did in 1D kinematics. So let's just do this as a 1D kinematics problem. So say that this is 1 meter. That hand would have to be pretty big, but so first thing we have to do in 1D kinematics is choose a time equals 0 instant, a time final instant, a position equals 0 location, and a positive direction. What do you want to choose as time equals 0? Yep, so it's dropped. And what about time final? Yep, when it hits the ground. Zero position, you could choose this anywhere, but yeah, I think I would always choose the ground, and I'd always choose the positive direction up. So that's what I'm going to do. So these are shown in the picture. And now the second step is to figure out what we know and what we want. We're just going to go through the list. We only have those 7 variables from 1D kinematics to deal with. Do we know time final? No, that's what we're looking for. Do we know acceleration? Yeah, that's 9.81 down. So since up is positive, A is negative 9.81. I'm going to be lazy and leave out the units in this calculation. Do we know the initial position? Do we know the position of the bullet at time equals 0? Yeah, it's 1 meter in the positive direction from 0, so that's positive 1. Do we know the final position? Yep. Do we know the initial velocity? It's dropped from something that's not moving, so VI is 0. And then final velocity? Unknown, right? We're happy without it, so I'll just leave it off. Look for one of the 3 1D kinematics equations that work here. And the one that works is PF is equal to PI plus VI TF plus 1/2 A TF squared. So we have that 0 is equal to 1 plus, since VI is equal to 0, this term is 0, plus 1/2 times negative 9.81 times TF squared. And so you get, 1/2 times negative 9.81 is negative 4.905. You can add that to both sides and you get 4.905 TF squared is equal to 1. So TF squared is equal to 1 divided by 4.905. Take the square root and you get TF is equal to plus or minus 0.455 seconds. And we have to choose, that's two answers. We have to choose one of those two. So which one makes sense to us? Positive, yep. Okay, so if you start a bullet a meter above the ground and drop it, it takes 0.455 seconds for it to hit the ground. So now let's do the calculation for a bullet that's fired horizontally and see, we're going to get the same answer. Let's see if we can sort of identify how it works. So for B, this is a bullet fired horizontally at 1,000 meters per second. I don't know, that's somewhere in the right ballpark. It's a nice round number. Again, this is going to be from a height of 1 meter. Okay. And again, this starts out 1 meter above the ground. Okay, so for 2D kinematics, what's the first step? Yeah, so we're gonna do these two things again. Time equals 0 and time final, and then we have to choose an origin location and a orientation of the coordinate system. Time equals 0 is going to be the instant it's fired. Time final is going to be when it hits the ground. For a coordinate system, I'm going to do what I do at least most of the time, possibly all the time. I'm going to put the origin on the ground beneath where the object is at time equals 0. And I'm going to put the y-axis up. So the origin location and the coordinate system orientation are shown in the picture. And now the second step is we have to go through, now we have 13 variables we have to think about. But we go through the list of variables, figure out what we know and what we want. Do we know time final? No, that's what we're looking for. Acceleration? Yep, acceleration is straight down in free fall, and that's the negative y direction. So ax is 0. There's no component in the x direction. Ay is negative 9.81. Initial position, that's the coordinates of the bullet at time equals 0. What are the coordinates of the bullet at time equals 0? 0x, positive 1y. So pix is 0, piy is 1. Yes. Y is what? Oh, the acceleration. The acceleration is, so the acceleration vector, if you draw it, is this, right, with a magnitude of 9.81. Our coordinate system is this. So now it's just a matter of figuring out what the components of this vector are. And there's two ways you can think about it. One is, the hard way is to say it has a magnitude of 9.81. The angle is 270. So 9.81 times cosine and sine of 270 gives 0, negative 9.81. The easy way is to just notice that it's on the negative y-axis. And, think about what the coordinates of the head would be. This distance is 9.81. It's in the negative direction, so 0x, negative 9.81. Do we know anything about the final position? We do know something about it. We don't know everything. We don't know how far away it's going to hit. It's going to hit a long way away. But we do know what the height is going to be when it hits the ground. What's that? 0. So P, F, Y is 0. And then the velocities. Do we know anything about the initial velocity? We can figure that out. Well, we weren't given it as components, but we were given everything we need to figure out the components. So what we have is a vector that's horizontal, and it's really long. It has a magnitude of 1,000, right? But so this is the tail of the vector. It's completely on the positive x-axis with a magnitude of 1,000. So what are the coordinates of the head of this vector? What's the x-coordinate? 1,000, positive 1,000. And what's the y-coordinate? 0. And so the velocity vector is positive 1,000 for x and 0 for y. Yep. That's a different thing. Yeah, so this is just, no, that's a different thing. That's just if something's dropped. But if it's fired or thrown or whatever, then you have to account for the speed that the launch process puts in it. Do we know anything about the final velocity? No. So this is it. Okay, so now we have to see if now we have to look through all 6. Question? Well, I think I mentioned this last time. I hope I did. So we do, in the back of our minds, hidden away in our brain, we know that the x component of the velocity isn't going to change. But don't write that down as a known, because if you do, it'll look like equations will work, but actually it'll be a dead end. So if you just pretend like you don't know anything about what the final velocity is going to be, and then any equation that looks like it's going to work will work. Okay. Okay, so now we have to go through all 6 of those constant acceleration equations. Look for one that's going to work. And I'll save you some time. The one that'll work is PFY is equal to PIY plus VIY TF plus 1/2 AY TF squared. And if you fill this in, it says 0 is equal to 1 plus VIY is 0, so plus 0, plus 1/2 times negative 9.81 times TF squared. And now if you compare this to the equation we had for the dropped case, it's the exact same equation. And the reason it's the exact same equation is since this initial velocity was completely horizontal, and there was no y component of that initial velocity, we had a 0 for the initial y component of the velocity, just like we did in the case where it's just dropped from rest. Okay. So we get the same equation, and if you have the same equation, you're going to get the same time. That's the same equation as before. And so time final is equal to positive 0.455 seconds. And we saw in the video that that happens in real life too. In reality, there'd be a small, tiny difference between these just based on the air resistance. Well, there's a lot of air resistance on a bullet because it's going really fast, but it's not going very fast vertically. And so it's being slowed down horizontally, but air resistance doesn't affect its fall time hardly at all. Okay, so the key to these two things being the same was that that bullet was fired perfectly horizontally. Okay, so let's say that now it's done a little bit sloppily and the bullet is fired angled up 1 degree. 1 degree isn't very much, you know. So how long does it take to hit the ground if it's fired 1 degree above horizontal? A height of 1 meter. Okay, so we're talking about this is exaggerated. 1 degree is a much smaller angle than I have drawn here, but this is what we're talking about. So the bullet's shot like this, and it's 1 degree above horizontal. Terrible picture. Okay. So what was yeah, 1,000 meters per second. So the thing to remember is the key to these two things being the same is that when you fired the bullet horizontally, the y component of the velocity was equal to 0. Okay? That was the thing to keep in mind. Now that it's being fired 1 degree up from horizontal, there is going to be some non-zero component for the y component of the initial velocity. And that's going to affect the time that it takes to hit the ground. Okay, so we have to choose these. Time equals 0 is when it's fired. Time final is when it hits the ground. Origin location is on the ground, right beneath the bullet at time equals 0. And the coordinate system is the y-axis up, x horizontal in the direction of the shot. That's all just like I did before. And now let's go through the variables. Time final is what we're trying to find. Acceleration. This is free fall. Our y-axis is up, so the x component 0. The y component is negative 9.81. The initial position, pix is 0. piy is positive 1. The final position, pfy, is equal to 0, and we don't know how far away it's going to hit. The initial velocity we can figure out, but we're going to have to calculate that. So to calculate that, here's the coordinate system. Here's the initial velocity vector. Then again, I'm really exaggerating that angle. This angle is 1 degree, which is way, way smaller than that. That's probably more like 15 degrees. It has a magnitude of 1,000. So that initial velocity vector is 1,000 times, to go counterclockwise from the x-axis, you go 1 degree. So 1,000 times the cosine of 1 degree, 1,000 times the sine of 1 degree. And that comes out to be, so this one is, the horizontal one is basically 1,000. I think you get 999.884. Okay. Like we saw before, to figure out the time, we're only going to use the y component anyways, so this won't come into it. But then what's the y component? Okay. So remember, the reason, so the x component is 999.85, and the y component is 17.45. The reason that if you fired the bullet horizontally, it hit the ground at the same time as if you dropped it, is that the y component of the initial velocity when you drop it was 0. Look at how big it is now. Even though that angle is tiny, 1,000 meters per second is so fast that this has an initial y velocity of 17.45 meters per second. That's like almost 40 miles an hour. So this bullet is going to vertically, like if all you saw is like the vertical shadow of what it's doing, its vertical motion is going to be the same as if you launch something up into the air at 40 miles an hour. That's how long it's going to take for it to go up and come back down. So it's going to go up, what I can't remember the number, but say 15 meters, you know, it's going to go up 40 feet in the air or something before it turns back around and hits the ground. So let's calculate the time. At that speed, that's exactly right. Because again, that x and y motion, they don't care about each other. It's just a matter of the y motions. So we'll use the same equation. Pfy is equal to PIY plus VIY TF plus 1/2 AY TF squared. So we have 0 is equal to 1 plus, this time we have 17.45 TF minus 4.905 TF squared. And I'm going to rewrite this as a hint of how to solve this. So negative 4.905 TF squared plus 17.45 TF plus 1. Yep, how do you solve this? Quadratic formula. And I don't remember if I mentioned this last class, but anybody who has a TI graphing calculator, if you come talk to me at lab sometime when I'm not busy doing something else, it takes 30 seconds for me to put a program in your calculator that does the quadratic formula, then you never have to think about it again. Look at how busy Grace is thinking about it. Okay. Oh, you're awake, just in time. Okay, so this is A. Negative 4.905 is A. Positive 17.45 is B. 1 is C. Plug that into the quadratic formula, and TF is equal to negative B plus or minus square root of B squared minus 4AC divided by 2A. And you get, I forget what the negative 1 is, but we don't care about negative 1s. There's a negative 1. I don't remember what it is. 0. That's the one we don't care about. And then the other one is 3.62. Look at it, it's spreading along the row. Everybody down there, be ready to fall asleep soon. Okay, so 3.62 seconds. So remember, when the bullet was fired horizontally, it took 0.45 seconds to hit the ground. Now, because you were inaccurate in doing it horizontally and you lifted it up 1 degree, probably that much, it takes over 3.5 seconds to hit the ground because it goes way up in the air before it gets to its highest point and then starts falling back down. Any questions about that? That's how long it takes to hit the ground. And if you wanted to figure out like how high it got at its highest point or how long it took to get to the highest point, you just have to say in your known values, your PFY, not your PFY, sorry, your VFY is equal to 0 because that's how you specify the highest point, and calculate PFY. Your TF would occur at the highest point, and go through the calculation and you can see how high it goes before it comes back down. Minus V over 2A. Yeah, but this starts at 1 meter. So you'd have to know where the minus V, if you know the function, if you know the equation for the parabola. Oh yeah. But you have to come up with the equation for the parabola. So don't do it that way. Okay, that's it. I'm going to hand out the quizzes.